If X follows the Poisson distribution of the parameters lambda, find the expected value and the variance. How do we find the expected value and the variance in this case? We are just given a statement. We are not even given the Poisson distribution itself. So the first thing we need to do is to recall the form of the Poisson, the form of this distribution, which is just of that. So this is the Poisson distribution. Then let's begin with the expected value. How do we find the expected value of the Poisson distribution? What we need to do first of all is just to write the formula of the expected value, which is just summation of all x, then multiply by the PDF. In this case, the PDF we have is a Poisson. So what we need to do from there is just to plug in the information that we have x, then this PDF will be just the Poisson that we have there. We have negative lambda, exponential of negative lambda, then lambda of x factorial. So here, what we need to do? What we need to do is just to expand this. And as we expand this, what we will determine where we are going to end is the moment that we're dealing with. In this case, we have the moment less than 1. So we are going to end on 1 when expanding this. Now, how do we expand this? So let's say, for example, you are expanding 3 factorial. How do you do this? So you would say 3 multiplied by 2 multiplied by 1, which is just the same as 3 minus 1. I want to write the 1 here. 3 minus 1 and 3 minus 2 and on and on and on up to some term here. Then you'll have 3 minus k factorial like that if you're expanding that. So this k shows the moment. In this case, our k is 1. And when we end, see that we have a factorial there. So in the video I made on the binomial, I didn't include this. I thought the student might get confused for simplicity, because these videos are not about, teaching students how to expand this. But I think in this video, I need to include that concept because it's very important to know if you don't know. So let's just expand this. So we'll have x, exponential of lambda x, and expanding this up to 1 will be x, then x minus 1, and we put a factorial by using this logic. But, well, it's pretty very easy just to master this, what we have here. Yeah. And to always remember that when we end, we have to put the factorial as well as respect the moment which we are dealing with. Well, what we do from here, notice that this term and that term cancels. Then we have this, which is just constant. So we can put it out, well, but before we put it out, I don't want anyone to get confused, so I just want to leave it like that, but I know that I'll take it outside. So this will be, I'm not taking outside anything here, so that no one gets confused, as we saw. So this will be just that, then remain with x minus 1 factorial. So what we need to do when we reach here, what we are going to do here is to make sure that this becomes a Poisson distribution. Of course, if you look at it, it looks close to the Poisson. You can be comparing it, but unless, the only thing that remains to make it look like that, if you notice here, x, and there's the power x even down there. But if you come here, you only have x, well, but here you have x minus 1. So to make it look as the Poisson, what we're going to do is, we're going to say lambda, we're going to introduce a negative 1 to there, so that this power and the down part be the same. But when we do that, we need to multiply it by lambda like that, so that this becomes that. So here there's a 1. When we multiply this, it just remain with that. And that means we have not changed anything. So we will have over x minus 1, lambda like that. So I didn't want to take this out so that you can see that, well, it's very, very similar to Poisson distribution. So we can now take out the constant. This is the constant as well as that. So when we take them out, we will will have let's put lambda there, and we'll remain with lambda x minus 1 over x minus 1 factorial, like that. So from here, what we'll need to do is just to make this closely similar to the Poisson. If you notice here, we have a single term here. So we're going to rate this equal to y, which is x minus 1, so that we remain with. So if these guys were inside, we are able to see that it looks exactly like the Poisson. So if we have that, then we'll have x, then lambda will be less than y, and here will be y factorial, like that. So this is just the same as exponential of lambda, like that. So what we're going to have is, let me grab some things. I'm not getting everything second time. So let me just say lambda exponential of negative lambda is multiplied by, because this term is just that, it's multiplied by lambda. Sorry, I'm supposed to write exponential lambda, exponential of lambda, positive lambda, not to go down. So it's exponential of lambda, like that. But this is just the exponential series. The exponential series, something like that. Yeah. So exponential series add up to 1. So what we'll have here is lambda multiplied by 1, and our final conclusion will be just lambda. So the expected value will be equal to lambda. But if this is too confusing, you can take this guy in, and notice that when you take it in, you'll have exponential of negative lambda, you remain with this outside. Then this is just an exponential, which is just a distribution equal to 1. Then you also get lambda, like that. That we can as well make sense. Well, let's turn to variance. So variance of x is given by expected value of the second moment minus expected value of this moment, mean squared. So we know this, but we don't know this. Well, let's compute this. But the identity to this is just expected value of x minus 1, like that, plus expected value, like that. So this, we know, is just the same as expected that we have in here, but we don't know this. So let's go on and compute that, what we don't have. I want to show you this way in this video, but of course there is another way of just going direct computing that. Perhaps in the future, in the next approach, I'll compute using that, so that in case someone might find this to be complicated, so that they can use the other one if this one looks to be complicated. So we'll have a Poisson here, like that. So I'll try my best to explain it in a way that is very easy to understand. So when we have this, we have forgotten to write the formula, but anyway, it's just one and the same, yeah. So if we have this, when we're here, what we need to do is to expand this up to the moment that we have here. In this case, we have x squared. So up to second moment, the k is 2. So what we're going to do is, just as we did, we're going to say summation of x minus 1 that under x, and we're going to have x minus 1, but we are not ending here. We have 2, end on 2, like that. And if you notice, this term and that term goes, so we're literally just going to remain with things inside. This time around, I don't want to pull out the constants at that state where I put them out. I want to extend a bit so that it makes sense of the other way I talked about. So we're going to say exponential of negative lambda x, we'll have x. Here we need to put a factorial where I just forgot. We have a factorial there. So let's work out this there. So we'll say is equal to, we want to make that a Poisson. So what we're going to do is we're going to say negative that, as we're writing that. We're going to introduce a lambda squared. And once we introduce that, we will say lambda minus 2. We let it take that power. Then we'll have x minus 2 factorial like that. And this, well, I've just cleared that space there because I know we need some space in the future. I mean, where we're going. Well, so I was saying, here, we can check out this because it's just, a constant. So we can have that. Don't worry if you're not there yet, you'll get the concept. So we're remaining with that, then that, and that down there. So what we need to do from here is just to make this look as closely as possible to the Poisson that we, the one we see most of the times. So what we can do here is just to let this term equal to y, this term equal to y. So if we let that term equal to y, then we'll have lambda squared summation of x, then that will remain. I don't want to remove it this time around. I want to show you that, which is the other way that I spoke about. So that will be y, and even here will be y. Yeah, y factorial. So if you notice this is simply the Poisson distribution, and any distribution is just equal to 1. So what we're going to remain with is just a lambda squared, like that. Because lambda squared will be multiplied by 1, and we're going to remain with lambda squared. So lambda squared is this expected value. That. So now we have all what we need to compute the variance. So that was a very good idea to clear this here. I see. So here we're going to put, let me just write the original formula first of all. Like that. Then this we said we can also write the identity of it, which is just, I'm just making a mistake here. It's nothing like negative. Someone might get confused. So we'll have x minus 1 plus expected value x that, and minus this, because we are just rewriting this. Expected value of x squared like that. Then this we know it's lambda squared, and this we know is lambda, close the brackets, then lambda squared like that. And if we remove the brackets, we'll have that minus lambda squared like that. And if you notice this and that cancels, then we'll remain with lambda just like that. And from here, we can see that the expected value lambda we found is just equal to the variance, because the variance we have just computed it's as well lambda. So with the Poisson, the expected value and the variance are the same. Perhaps that's why they just gave us this statement to show that parameters is just lambda. In this, the parameters are supposed to have the expected value and the variance, but because they are the same, well, we can simply write like that. Why should we suffer? Thank you. Well, we can just write like that. It's one and the same because they are all the same. But I was thinking of something. Well, if you wanted to watch this video for the expected value and the variance, well, that's it. But if you have a bit of time, I wanted to show you how to show that Poisson distribution is actually equal to 1. In my videos I uploaded recently, I didn't upload that, but I've just thought that is very important. In this one, I want to show you that this distribution of the Poisson is equal to 1 when we sum up. So I'll do that just in less than 1 minute. So this will be summation of, we just put the distribution itself, and lambda x factorial like that. And because this is a constant, we take it out. We know it's a constant because we're dealing with a variable x, and this term has no x, so we're remaining with that factorial when we take that out. So if you notice, this is the exponential of lambda here. So this is exponential of lambda there. So we will have exponential of lambda, negative, and exponential of lambda, like that. And this, if you recall, that's the exponential series, which add up to 1. And if we share, then we have showed that Poisson distribution is just equal to 1. Therefore, it's a distribution. Well, that's it for this video, guys. Thank you for watching. See you in the next approach. But don't remember to hit the subscribe